Welcome to Megasquirt Training Part 11. In this video, we're going to be taking a look at our fuel correction tables. We're going to have a lot to learn, so let's get started. Okay, so let's jump into this video and talk about our fuel correction tables we're going to be working with in our Megasquirt software. So we're going to be finding that the Megasquirt is going to be based around a manifold air density table. And this is going to be correlating our temperature versus density. So we know at the colder air temperatures, our density is going to be increasing. We need to deliver more fuel. And at the hotter temperatures, we're going to have less dense air, so we have to do less fuel delivery. So we're going to have a table that's going to take this into account. And it's going to be based on the ideal gas law. We learned about that in EFI basics and why that's important. So it's going to have this built into the software. Now it's going to take that a step further, and it's going to be comparing the engine coolant temperature and the intake air temperature against a biasing table. Now it does this because if we have an engine that's idling with the hood shut, we might find that the intake air temperature is going to be very, very high. It's going to report something like maybe 160 or 180 degrees on a very warm day. Now that doesn't mean that the air entering the actual engine is going to be that hot. We're going to be absorbing a lot of the heat coming out of our engine as it's having that under hood temperature being built up. And that's going to create a false reading into the ECU. So we have to compensate for that. We have to block out that kind of density or false reporting density coming in the ECU, because what's going to happen is we're going to go ahead and pull too much fuel out, and we're going to be finding that the engine starts to run lean. So in order to get around this, we have to use this biasing table we're going to be taking a look at in this video. We're going to be seeing it's very important to set up right. I'm going to be giving you some decent settings to go in and get your tuning started with. So without further wait, let's jump into the video so we can check this out. Okay, so let's get started here. We're going to be taking a look at our air temp corrections or density corrections in our fuel strategy, as well as looking at our injector dead time values and our deceleration fuel cut in this video and how it all applies to our tuning. So the first thing we're going to be doing here is jump up into basic load settings. We're going to be going down to manifold air temp air density table. We're going to be seeing that we have this table here, and it's going to be based on air temp versus a correction. Now this table is based on the ideal gas law. So we know at a particular temperature what is going to be the air density, and then as the temperature changes, if we get to the colder temperature, we have to have more correction because we're going to have more density and the air is going to be more dense. And if we get to the hotter temperatures, we're going to have less fuel or less correction here because our air is going to be less dense. So when we're in our speed density, baro and speed density, or alpha N style tuning, we utilize this mat air density lookup table to provide us that density or air density calculation into our fuel strategy. Now if we're in the mass airflow based, we're not going to be using this table at all. It's not going to be referenced. We don't have to worry about it. But in our speed density modes, we definitely have to worry about this. And the values that are in here are going to be very, very accurate, and we don't have to worry about changing them in most all situations. This is, again, based on the ideal gas law, where PV equals nRT, or pressure times volume, is equal to our universal gas constant times the temperature. And we're going to be knowing that relationship of how that all works. We went over that in EFI Basics and EFI Advanced. So that should make a lot of sense right now. And if you're confused at all, go back to the EFI Basics and Advanced courses. I walk you through what all that means and why it's important. So this table doesn't have to be adjusted, but the purpose of it being here is to provide the density calculation and correction for our speed density style fuel strategies. So if we close this and jump into our next section here, our MAT/CLT correction. Now this is something that's a little bit of a foreign concept to a lot of people, but this table is very, very important in our speed density calculation. Now in speed density mode, we are estimating, or we're calculating the air mass. So in this case, we use our intake air temp sensor to provide us an air density that's entering the engine. The problem is if we have our intake air temp sensor mounted onto our intake manifold, and if we're driving around and we get a lot of heat soak, our intake air temp sensor is going to heat soak as well. And then that's going to be providing a much higher air temp reading to our ECU. And in the fuel calculation or fuel strategy, that's going to go skew our data up and skew results up. So our VE table is not going to be as accurate because as it's coming in reporting a higher than actual air coming into the engine, because we have, again, our intake manifold has that heat soak going on. As we have that effect going on, it's going to be reporting that we have the air coming in is going to be much less dense. It's going to be saying it's hotter than it actually is. And that's going to be a problem because it's going to throw off our calculation. So what you might notice at a given coolant temperature as you're driving the vehicle, and let's say the first 10 minutes of your driving, you're going to be noticing that if you don't have a good correction or compensation factor using this kind of table here, you're going to be noticing that your fuel trims and all of your fuel coming out of your table was perfect. So you've tuned your main fuel table, your main VE table, everything is spot on for your air fuel. And then as you drive it more and more, you're noticing that your coolant temperature remains the same, but you come down to a stop and you let the car heat soak a little bit, maybe for 5 minutes, you're just sitting and idling. You're going to be noticing that if you look at your fuel trims, or if you watch your wideband, if you're in open loop, you're going to be noticing that your air fuel starts to change a lot. And that's because this air temperature is going to be reported falsely to the ECU, and we're going to have a false air density reading, and then our calculation for that volumetric efficiency for that air mass is going to be incorrectly reported. So that's going to be a major problem. So this table here is going to allow us to have a biasing factor from our air temperature compared to our coolant temperature. And it's going to be allowing us to account for that heat soak or that false heat soak under low flow conditions or low airflow conditions coming in our engine. So if we look at something like a zero airflow, so we had no airflow coming in our engine, it was just the air temperature was mounted into our intake manifold, and the engine temperature itself was the only thing other than ambient that would have an influence on the temp sensor, we're going to be finding at zero airflow, all of the air temp sensors heat soaking or reading would come from the actual engine coolant temperature. But once we get moving, and once we start to have more air rushing into the engine, we get out of the zero airflow condition, we're going to be finding in those conditions that we're going to be reading more towards the actual air density coming in the engine because we have a lot of air coming in, rushing over that air temp sensor. It's going to be a lot more accurate. And if you ever looked at a data log for if you're driving in heat soak and you start to drive for 5-10 minutes and you have enough air coming over the car and you're sucking air into the engine, you're going to be seeing your air temperature starts to drop if your air temp sensor is mounted into your intake manifold. And that's significant because then you're going to have more accurate representation of your air density. So what we would want to do in this table, if we open up our axes here on the corner, we're going to be seeing its flow versus a correction. So at these low flow amounts, we might want to have a very high value, something like 80%. And as we go up here into the higher flow ranges, we want to drop off to 0%. We don't want to have any correction because at those higher airflow amounts, we're going to be reporting our density corrected here, or correctly reporting our density. So what we're going to be doing here, we're giving an error message. It dropped me offline here. I'm just going to click yes. We're going to be seeing here, looking at this, if we go to our next data point, we might have our next data point here at 30, and then our next data point here at something like 10. I'll click burn, so it accepts those changes. And when we've done that right there, we can see right off the bat our injector pulse width here has changed. It went from about 6.7, 6.5 to 6.0 milliseconds. I haven't made any changes to my main VE table, and it's going to be ignoring or having less influence here from our manifold air temperature, and it's going to be looking more at my coolant temperature, which here is 180, and that's going to be a little more accurate representation of what's going on. Now, as I change my air temperature, if I go up and I have a hotter air temperature, you can see here if we increase it here, we're going to be seeing that our pulse width here, let's turn it down a little bit, our pulse width decreases, and that's going to be normal because it's going to be coming from our air density table here. We can see our air density correction showing that it's taking out approximately 17. A value of 100% is going to be no modifier. A value of 83, 84 is going to be 16, 17% negative, taking out 16 to 70% fuel. And that's why you see that the injector pulse width dropped. But in this situation, it's going to be looking at this low flow. You can see our bubble here is on this lower flow level because we're at idle, and we're showing what our map sensor is reading here. And we're going to be calculating a lower flow value, which again is going to be our load times our RPM. So if we multiply these together, we're going to get this approximate value, and that's how we get the reading here in flow percentage. It's going to be having less influence on our manifold temperature compared to our coolant temperature. So we're going to be having this less effect of the heat soak. Now, as I start to drive and as I start to operate my engine and I come back into this situation, maybe my air temp cools down a little bit, we're going to be noticing that our pulse width is going to be much more consistent. Our fuel is going to be much more consistent. It's going to represent our air density much better by setting our table up like this. So this table is a little bit confusing, but now that you understand how it works, it's going to be there to compensate for a false air density reading from a heat-soaked intake manifold, and you're going to be populating it something like this. This should get you started. I always recommend that you go and fill out the table like this to begin with, because if you go in and leave this table 0, you tune out your VE table. You're going to have to go in, if you want to go and configure this, you're going to have to go back in and start to touch up the VE table. It's going to be changing the fuel delivery to the table or to the engine because you're going to be correcting that air density model. So it's always good to populate this before you do any kind of tuning and you set this up. Let's close this out. So let's jump into fuel settings now. We're going to be taking a look at our injector dead time. So this is pretty straightforward, but it's going to be differing from other standalones. It's actually going to be a really simple way to provide our injector data. If we look here, injector dead time at 13.2 volts, they want it in milliseconds. So generally speaking, we can see down here, they say typical value here would be 0.7 milliseconds for a low impedance injector, 0.9 milliseconds here for a high impedance injector, and then a low impedance injector with a resistor. We're going to be seeing, it's going to be showing here, or 0.9 milliseconds for a high impedance injector or a low impedance injector with a resistor pack or a resistor in line. So it's going to be giving you some values if you don't have any idea what your dead time value should be for your injectors. Now, we know that proper injector data is really key to making everything work right. If we have a data sheet from our injector manufacturer, we definitely want to utilize that at this point. So let's jump in here. I have an injector dynamics data sheet open for ID 1050X injectors. And I'm going to be assuming I'm running at 3 bar of operating pressure, or 43.5. That's pretty standard operating pressure. And it wants my dead time value at 13 volts. So we can see 12 volts is 1,125 microseconds. 14 volts here is at 925 microseconds. So if I'm looking at the data point between these that we don't have, it's going to be roughly 1,025 milliseconds, roughly. So we would go in here to our table and we would type in 1.025. This is in milliseconds, those are in microseconds. It's just the difference of our units. We have to shift our decimal place over 3 here to the left. That's why we get 1.025. Now, it also wants our battery voltage correction in our millisecond per volt. And that's going to be different than what they have here. And because we have our data sheet, we can actually figure out what that's going to be. So if we're looking here, going from, let's say, our 1,125 at 12 volts, and if we're going to that 1,025 at our 13 volts, we're going to be seeing it's approximately 100 microseconds or 0.1 second difference in our jump in our, let's jump back in here, again, in our millisecond to volt. So we would type a value of here, let's go in here, of 0.1. And that would give us the differences here as we're kind of going through our voltage points here. So every let's jump back in here one more time. Every millisecond per volt, we're going to be seeing a 0.1 millisecond per volt change. And that's going to be something very significant. And again, this is going to be in milliseconds, not in microseconds. So this would be 100. Looking at our table here, it's going to be 100. So if we have a data sheet, we can definitely calculate that. And it's going to be very important that we go in and populate this with the correct data. So this is going to be drawing, or assuming it's drawing, a linear line between our data points on our chart or our table here that we're giving us. So if we're able to draw a chart, we're going to be seeing at the low voltage, it's definitely going to have a larger jump here. We can see between 8 to 10 volts, we're going to be seeing a much larger jump. If we're looking, let's say, between 14 to 16, we're going to be seeing a little bit less of a jump. So this is going to be looking just at a kind of an overall linear scale of operation. So if we're at really low battery voltage, this may not be enough of a compensation right here to draw a nice linear line, because it isn't a linear line. So we're going to make the best of what we have here. If you find that your VE table, as you're dialing in the values, just doesn't seem to be right, you could always go bump this battery voltage correction here up and see if that goes and allows you to have a little bit more accurate VE value. So if you have too low of a value here, you might find that you have to go and increase the VE values. Let's jump in here real quick. We'll talk about that in our VE table here. We're going to be noticing that we have to go in at idle here. We might have to go and really increase the values to something like 60 or 65. We might see that all the values here are something very high, which may not be accurate. And that's going to signify that we don't have the injector data correct, because most of the time we're going to be seeing that this should be between 40 to 50 in the idle range. So it's going to be signifying that that could potentially be a problem. So be aware if you're entering your data in here, and you notice that you have to skew up your VE table that you might have to tweak some of these values here. It might not be perfect, but we should be able to figure out this injector time or dead time at 13 volts, and then this battery voltage correction here might have to be tweaked. So let's go ahead and burn that. Let's burn these changes here, and then we'll jump into our last section we're going to be checking out. Let's close this as well. We're going to be seeing here, let's close this out. We're going to be seeing under fuel settings, we're going to go into overrun fuel cut, and we're going to be seeing that we have this overrun fuel cut. This is going to be our deceleration fuel cut. And we want to use this because we don't want to constantly pump fuel when we lift our throttle. So if we're driving, we lift off the throttle. On a normal OEM car, we're going to be seeing that the wideband is going to be going dead lean. It's going to show that it's full lean. As we get back on the gas, it's going to go and richen up again. And that's for economy purposes. So we don't want to waste fuel. That doesn't make any sense. So normally in the base maps, you're going to be seeing this is set to off. I suggest at first you go and tune with this off. Once you've tuned your main VE table, then you can come back here and turn this on. And we're going to be setting up these parameters here in correspondence to what we're seeing, how our engine is running. So for example, let's kind of talk about everything here and make a bit of sense of this. We can see the RPM greater than. Now we want this higher than our idle RPM. So let's say our idle here is at 1,000. I would want to set this to at least 500 to 600 RPMs higher than my idle speed. Now in some cases, if I have a lightweight flywheel, I might even want to set this 1,000 RPMs higher. So let's assume that I have a lightweight flywheel. I'm going to set this at 2,000 RPM. Next, we're going to be seeing and map lower than KPA. We're going to be noticing here at idle, I'm roughly 40 KPA right now in my map sensor reading. Now when I lift my throttle, we're going to be noticing that this map sensor reading might go to something like 20 or 25 KPA. It's going to go to the lowest vacuum possible. So N map lower than, we might go and set this to something right around what our idle vacuum is at. That should be sufficient to get started. We might be even going a little bit lower. So if we have a big cam installed in our engine, let's say we're pulling something like 65, 75 KPA, so we have low vacuum, we might have to go in and set this something like 50 or 55 or even 60 KPA. So depending on what your engine's pulling in vacuum, again at idle, you can reference this. You can also watch during a data log or as you're driving down the road, lift your foot off the throttle at say something like 3,000 RPM, see what the map sensor is going to read, and then go from there. Then you can go and tweak this value so it makes a little bit more sense. We see N TPS lower than. Now this is important because we don't want the deceleration fuel cut potentially kicking in when we're driving under normal driving conditions. It's going to be shutting off the fuel injector, so it can create a stumbling effect. We want to have this low enough so that it's not going to be a factor, but it's still going to kick in when we lift our throttle. So we want to go in here and set this as something like 1 to 1.5%. I'll set this at 1% just so I know for sure it's going to be essentially when I'm off the throttle, I don't have to worry about it. And coolant temperature higher than. This is going to be associated with letting our engine warm up before we let the deceleration cut turn on. This is very important because on cold starts, if we have an idle assist, if we have an idle control motor that's going to go and idle our engine higher, if we have this set at something lower, let's say 1,500 or 1,600, and we have our potential idle speed on that cold start condition at something like 1,500 or 1,600, we're going to have a conflict here. And what's going to happen is, depending on how we have these conditions set up, we're going to have our deceleration fuel cut turning on when we're trying to have our cold start idle. So we're going to be noticing that it's going to cut the injector off, turn it on, cut it off, and we're getting a surging idle effect. And that's going to be really annoying, and we want to avoid that. So what I would suggest here is go and set this up to something right below where your normal operating temperature is going to be. So if your engine comes up to temp around 170, 180, that's to something like 150, 160. That way you don't have to worry about it kicking in on a cold start and creating problems for you. Now this after delay in seconds, this is going to be when you transition on and off the throttle a bunch of times. We don't want our deceleration fuel cut constantly kicking in. So it's going to wait for this long if we're having a lot of transitions, lifting throttle and coming back on. It's going to be waiting this much time for the deceleration cut to go back in and turn on again. Again, this is needed to provide a smooth driving experience. So depending on how much you're on off the throttle in a low speed condition, you can tweak this value here to turn the decel cut on and off how you'd like. We're also going to be seeing delay EGO after fuel return. Now if we're using our closed loop fuel correction, we're going to be looking at in some future videos, this is going to be how long we're going to go in and wait until we're going to allow the actual fuel correction to start going again. So once we lift our foot off the throttle, it's going to be shutting off the injector. What you're going to be seeing on your wideband is that it's going to show full lean. Now we want to wait at least 1 to 1.5 seconds in order for the closed loop control to turn back on and start trimming again. Now this is important because if we're trying to go and turn our closed loop control on, we have this at 0 time, and we get right back on the throttle, it may have a false lean condition reported because our wideband hasn't picked up our fuel being injected into the engine quick enough. So I usually like to set this at something like a second. Let's go back in here. At something like a second. That'll give me ample time to allow the fuel control to turn back on and not have a false lean condition and go in and try to add a bunch of fuel correction under closed loop. That's going to be something that we want to avoid. Now we also see fuel return when RPM less than. We usually want to set this about 200 RPM below or greater than, so I'm going to set this at 1800. That way we have a hysteresis effect going on when it cuts and when it can turn back on. And we always want to make sure, again, if we have a lightweight flywheel, set this about 1000 RPMs higher than your target idle speed or your warm idle speed. If you do not, what's going to happen is as you lift the throttle and you're coming back into idle, if you set it too close to your idle speed, you're not going to have enough time for the injector to turn back on and then provide fuel and not stall out. If you have it too low, you're going to be seeing that you probably have stalling or the engine's going to bog down as you're coming into idle. So we want to avoid that. And we want to set it to at least 1000 RPMs higher, again, with a lightweight flywheel. Under a non-lightweight flywheel, like a normal weight flywheel, you might want to set this to at least 600 RPM. But that should be some good guidelines. These should be pretty much spot on to get started if you're using your decel cut. But I always suggest that you leave this off, tune your main VE table, come back in, then turn this on, then dial it in, and then you'll find that it's going to be much more effective and it's going to be much easier to tune your VE table without having to worry about this, potentially creating lean conditions and having to worry about that as you're dialing in the curve, especially at the low vacuum portions where this has the more potential to kick in that VE table. Okay, so that wraps up Megasquirt training part 11. In the next video, we're going to be taking a look at our starting fuel. We're going to have a lot to learn, so I'll see you in the next video.